We'll think about it.
So now Deepanjan is talking to everybody in the department, like who will be available there.
Homework 10. There's also a request. Homework 9. Could you resubmit for those whom I've graded, and I forgot to put the points on detour.
Yeah.
All right. Is that something that you noted?
Yeah.
Yeah, please. I forgot. That was my fault. So some feedback. Sorry for the
Only the
inconvenience.
graded one.
Yeah, graded one, just so that I can put it on detour. So that's my fault. I think there should be only 2 of you who did that. And, probably because you requested for the graded ones right before the exam, so I was in a hurry. I forgot to put it. But nevertheless, my fault. So I was grading your how's that called? The take home or repeat part. There was a take home part, but there was a repeat part for the exam, and I was not satisfied, even though the solution was out. I think I would say I was satisfied with Deepak's work, and Ain makes it so concise that it's not very clear how he got it. But apparently, if I go with this work, I think Deepak and Ain seems to have understood Green's function, but otherwise, in my interpretation, it doesn't really mean that you don't understand. From my grading interpretation, none of the others understood the key part of Green's function. So that was very disappointing. But then I also probably was too quick. So what I thought was that today's example, I will somehow bring in the Green's function, so it will go through that. It also means that the final exam, there's a good chance that I'll ask Green's function, because whatever you guys are missing, that's what I would ask. So note that at the same time, it is harder to ask questions on Green's function. Typically, they're longer, but I will find ways to do that. So that's some comment. And yeah, so and then there is final exam. Because of this performance that I noticed, I decided not to have our breakfast outing on the day of the final exam itself. I think we should have the exam. There will be a good bit of take home component to that, but I want to leave the room open that if I need, I have it. Exam. There's a good chance that it might be only one question or so, but I don't know that as of now. Okay, so we leave the Friday, December 12th for the exam itself, like December 12th, Friday, 8 10 a.m. And that leaves us with the idea that there was a breakfast that you wanted to have. So I'm open with any other day. Most of the days, no, I shouldn't say that. Yeah, I teach also. So can we quickly, in the next 3 minutes, come to have a very good suggestion, and everyone agrees to that? Yes.
Why would we using any dessert?
After. Yeah. So after the exam is not a good idea. What about Thanksgiving? Is it, how many of you are away during Thanksgiving week, the whole week?
Yeah, big enough.
Yeah.
Maybe Monday.
Okay, so one of them is gone. So
If you go on Monday, then we can arrange on Friday evening.
or Saturday.
Other again,
Friday evening, Saturday is okay, I guess.
but you said it's going to be away.
Yeah, it's fine. I don't need to ruin anybody else's.
No.
Oh, when you are leaving,
I'll be working.
When you are leaving.
All the Thanksgiving break.
Yeah, but he's not there.
Yeah.
So if
I'll-
one of us is not there, let's just drop it. Let's not have it during that time. That's the best. Okay.
We can do before Thanksgiving break, like a Friday or Thursday.
How?
That should be.
I won't be able to, if it's during the school day, I won't be able.
Okay, you are free on Saturday, Sunday?
Cause I work from starting at 10 on the weekends. So it'll probably have to be during finals week, just one of those mornings. None of us have an exam. In the mornings, any of those days.
Yeah, I will not have it on final exam week because it might interfere with any one of your finals, and if you hurt your final, it's very easy to, even if there is a small feeling in your mind that, oh, it was because of this commitment that I have, I think it's a good idea not to do it on the final. So final week gone, Thanksgiving week gone, working days gone. So we have one weekend before the final.
What after the exam?
That thing said,
No, they right after the exam.
oh, right after the exam, good point. Lunch,
Yeah.
Yeah, that should be okay.
I have an exam during from 2 to this, I think it is 2:45 to 4:45. But between 10 o'clock and 2:45, that's sufficient time, I suppose.
I think so.
Right? Yeah, good solution. Yeah, non-trivial solution. Yeah, good. Yeah. Okay, so tentatively just look for conflicts. So what is it? How about noon, right? Or right after the exam, can we walk down?
After the exam is okay, we can complete the exam, submit the paper. we
Is
can
that
go.
easier, or you want to go and come back? That seems harder, right? Just after the exam? So
Even go and back is like a harder.
Yeah.
you guys
Then-
live 200 meters, really.
For me, okay.
So 2:30, 10:30 AM, December 12th. Fisherman, yeah, breakfast.
Okay, bring from home or we are going to restaurant?
Let's go to the, bring from, no, not bring from home, that will, then you will be cooking all the time, then your exam will be.
We'll bring both of them, food and.
No, we can.
Yeah, I think, I made you guys work so much, so I'll kill some money from mine. Okay, I think that takes care of
After
it.
the final, we'll get one question in class and then.
I don't know that. I don't know that. It could be at least one question, and yeah, I really don't know. It could be completely take home also.
Yeah.
This week, I think I want 3 questions in class because I'm really not satisfied after grading your makeup of the midterm 2. I was not satisfied. I think except as I said, Deepak and Payne's work, I was not satisfied. But that doesn't really mean much because most of the time, what you write may not be what you have worked on. So that's the impression I found. How about that? So, okay. Okay, let's do spherical harmonics. That's what we were working on. This is broadly the idea of special functions. One of the tricks that is that comes out very handy with this is what we did in the exam last problem. So you notice that you did an integral where you technically did not do any integral, you just played around with the sum. You changed the order of the sum and suddenly the integral got done. Those kind of tricks come out very handy even in solving differential equations. So that's what I want to at least convey at that point. one of the important special functions is spherical harmonics. So give me any function which is whose domain is on the surface of a sphere, which has spherical coordinates theta and phi. That can be expressed in terms of spherical harmonics. That's the idea, but we have to define our spherical harmonics. That's what we are doing in here. So usually they are defined as notation, maybe first is notation. Like I motivated them last time. L, M, theta, and phi. L goes from 0, 1, 2, all the way to infinity. M is less than plus L, greater than minus L. And theta and phi is on the surface of a sphere. So theta is phi. This is exactly the latitude and longitudes, except that the latitude that we talk about uses equator as your reference point. If you use North Pole as a reference point, then it's a spherical polar coordinate. The generating function for the spherical harmonics is we write 1 over L factorial in terms of let's say R hat. Notice there are two vectors here, A and R hat, and there is an angle in between. Right? So the only thing it depends on is the magnitude of A and the angle between those two vectors. So this whole spherical harmonics is practically written in terms of that. Remind yourself that if you have two vectors, so this could be R, and this could be your R prime. And if this angle had theta phi in it, and this had theta prime phi prime in it, this need not be in the plane. One of them could be coming out of the plane. Two vectors, there is a unique angle gamma. Cosine of gamma is equal to, in terms of theta and theta prime phi prime, what is that equal to? In terms of theta phi and theta prime phi prime, what is the angle gamma equal to? We did this sometime back, might not have registered. So vector R, let's say vector R half is equal to sine theta cosine phi in the I hat direction plus sine theta sine phi in the j hat direction plus cosine theta in the k hat direction. And the same thing with primes. So this is theta to theta prime and phi to phi prime. If I had a cosine of gamma, that's nothing but vector R hat dotted with R hat prime. And what will that come out to be? I take the dot product of these two vectors. How much will that be equal to? Rings a bell? So you get sine theta is common than sine theta prime. So sine theta prime. But then cosine phi prime, sine phi prime, they combine together. That's cosine of phi minus phi prime plus sine theta prime. That's what we are talking about. So this vector that we are having in here, that has an angle in between, which has this feature, just reasonably messy, complicated. And we are going to find a way to decouple them. So that's the main idea, that can you decouple all these things. For that, what we said was, we will write this in terms of a square. So a square being 0, so we are going to take a special vector. So usually we, when we are doing a vector space, the coefficients of the vectors, including the unit vectors, are all real, right? I hat is expected to be, it's a symbol, but nevertheless, we understand that it is 1, 0, 0, right, in 3-dimensional space. But it is possible to go into complex features, and let's say that we are talking in terms of vectors. E1 is equal to I hat, not a good idea. I hat will repeat itself, so plus I times y hat, and E2 is equal to x hat minus I times y hat. Here, I is square root of -1. If we allow those features, then it is possible to talk about two vectors whose square is 1. Otherwise, if you are in real number space, a1 square plus a2 square plus a3 square, that's impossible to be equal to 0. But if you're in a complex space, that is possible. And what we said was a1 plus a2, let's say that's equal to y minus square, and a1 minus a2, that's equal to minus y plus square, and a3 we said is y minus y plus. That was our construction, and we want to put this back. I can also say y a1 and a2, right? So a3 is already known, so a1 would be y minus square I add, so this is y plus square over 2, and a2 is y minus square plus y plus square over 2 pi. Just a complex number construction. Use that to rewrite this. So I have 1 over L factorial and A dotted with R. So that is A1 multiplied by R hat is somewhere here, right? So that's multiplied by sine theta with sine phi. So that is y minus square minus y plus square divided by 2 times sine theta sine phi. So sine phi plus y minus square and finally we have minus plus times sine theta raised to 3. So that's a very blunt a way of putting this. But now let's process this. The claim is that this will be defined to use YLM. So what is going to be the definition of YLM? If I were to process this and I want to write this in the following form, this will be used. Let's say write this summation. You can see where the summation is coming from. This is a binomial expansion. M is equal to minus L plus L plus L plus M. So this is just a definition I'm writing. No, this goes into the definition. My bad. This is going to be the y m either 5 and put a 4 pi also. I think so. Let me just make sure I'm not mess.
It's under root, maybe 2e 4 pi by 2e plus 1.
Is that an under root? Yes, that is. Good, thank you. And there is the L factorial also. Good. So the idea is, we want to write YLM in terms of this theta phi, y small script, y plus and y minus, we want to pull out, rewrite the sum. So that's the basic idea. It's mostly algebraic, but it takes a little effort. So let's do that. So clearly we want to collect them in plus and minus. So let's start from here. So, let's take out the 2 raised to L. That comes out, and I have y minus square. I'm going to collect all the y minus squares. There's one here, one there. There is a sine theta. Both of them have a sine theta. This is a cosine phi with a positive sign, and then the I goes to the numerator, that becomes a minus, and this is exponential minus I phi. Right, so that's the y minus square, and y plus is minus y plus square sine theta e raised to I phi, because both of them are minus, because when I goes to the numerator, it is a negative sign. So I've taken care of these two. And when it comes to this, I've taken out a factor of 2. So it is 2 times y minus y plus times cosine theta raised to. I think this is where we were last time I introduced until here. Let's process this a little bit more. Let's bring out a y minus out. So 1 over 2 raised to L factorial. Let me take y minus square out. Let me also pick out an e raised to minus I phi. And in the denominator, let me take out a sine theta. All this is being pulled out with a power of L, because overall there is the power of L. So when I pull out a y minus, this leaves it just 1. Sine theta is, I pulled out a sine theta in the denominator, so that makes it sine square, I suppose. Yeah, because and e raised to I phi has gone out. Did I do this correct? I think so. Minus y plus square, y minus square. I pulled out an exponential of minus I phi, so let's e raised to minus 2 I phi, and I pulled out a sine theta out. So this is sine square. And plus 2 times y minus square is out, so y plus over y minus, and there's a sine theta. Taken from the denominator taken out, so the sine theta, the sine theta.
There should there be an e to the I5 on that as well?
Yep.
On the third one.
Oh, yes, because I pulled out a minus 5. That tells me that I should pull out the opposite. Let me try that. So if it's okay, I'm going to pull out a y plus. Y plus comes with an exponential of I5. So let me try this. So
First one change.
hmm?
First one what?
Yeah, so give me a second. So this is y minus squared over y plus squared sine squared theta e raised to minus 2i phi. This one is plus gone, here is I phi gone, so that's minus sine squared theta. And this will be plus. And the denominator minus sine theta, and I add e raised to minus. Well, and I do one more thing. I make a cosine square theta and plus cosine square theta. Okay. The idea being that this is minus 1, so including the sign, that is a minus 1, and this can be combined together as a whole square. So let me try to do that. Factorial plus square e raised to pi sine theta pull the minus 1 on the other side, so I can see that this is equal to y minus over y plus times sine theta e raised to minus I5 plus the square this, it gives you this. Square this, that gives you cosine square, and the cross term is nothing but this. So that's a straightforward algebra there. And now the question is, can I process this? Remember, I want to write this as a sum somehow, right? So write it as a sum. And for that, I'll make this simpler. Let me define a function of this kind, like L x plus a is equal, or let me define IL of x is equal to x squared minus 1L, and immediately IL x plus a is equal to x plus a the whole square. This one. Maybe write this in the form a plus x. And that is of the same form here, right? If I were to see cosine theta as x and this whole expression as a, that has that structure. So if I want to start from here and write it as a plus a, it is usually a translation, and translation is captured usually as exponential. Remember, f of x plus a is equal to, I think we used this in a couple of lectures before. This is a times d by dx of f of x. So this is basically f of x. Okay, this is a way of writing Taylor series. Okay, derivative, derivative, derivative. So it's just a form, a symbolic way of writing Taylor series. So if that is the, and this is also equal to, let's say, n equal to 0 to infinity, a raised to n n factorial times d by dx raised to n of f of x. Right? That's the real Taylor series. That's just a way of symbolic way of writing Taylor series. But let's do that. So this is equal to n equal to 0 to infinity, and I have a raised to n over n factorial x to n. I have x squared minus 1 to l. There are n derivatives, and the highest power of this polynomial is 2 times l. So any derivatives more than 2l will only give you 0. Right. So for example, if you have x raised to 7 plus bx raised to 6 and so on, if I were to take d by dx raised to 8, how much is that equal to? That's 0, right? So that once the power of the derivatives goes higher, it gives you 0. Use that property to change the upper limit to 2l. There is no need to go to higher derivatives. The Taylor series ends after a while, right? There's an upper limit there that is 2l. Once you realize that, it is now we are working on the sum, and in the construction or in the definition of my spherical harmonics, it's running from minus L to plus L. I want to change this sum instead of going from n equal to 0 to 2L. So let's define m to be equal to L minus n. So when n is equal to 0, m is equal to L. So instead of summing over n, I'm now summing over m. So it is plus L. And when n is equal to 2L, it becomes minus L. So I'm summing in reverse if you want, plus L, and then I'm going in the lower orders. That's perfectly fine. So this is n is equal to L minus m. So this is L minus m factorial d by dx. L m x squared 1 to L. If there is a sum, it doesn't really matter in what order you sum. Like whether I do 1, 2, 3 or 3 to 1, it's the same. So if I change this order, everything will remain the same. So this is the same as m going from minus L to plus L. That's just a x is to L minus 1 x squared minus 1 is to L. And that's practically takes me to a good spot, because now I have got a sum involved in there. So I'm going to write this as, let me see if I can capture this. Let me not be lazy. It's equal to 1 over 2 raised to L factorial y plus square e raised to I pi, and that is sine theta raised to L.
Yeah.
Did I miss something? Oh,
So the limit is here like plus L to minus L, but that side minus L to
yeah, if I'm adding 3 numbers, so it's like saying sum over, let's say m equal to minus L to plus L of, let's say, FL, right? So this is the same as let's say minus 2, right? Minus 1, make it simple, right? So this is f minus 1 plus f of 0 plus f of 1, right? That's the same as f of plus 1 plus f of 0 plus f of minus 1. Order doesn't matter in the sum. And then I rewrite the sum as m equal to plus plus 1 to minus 1 this time. Or you can say, yeah, so that's it. Let me not confuse further. Okay. So this is the same as f of L again. So I resubstituted a parameter there, but the easiest way to say it is that it doesn't matter. Comments? Okay. So I'm going to, so this is what we sort of found a summation for. So let's write that as a sum. So this is the sum of, I'm going from minus L to plus L. A is this quantity in here. So it is y minus sine y minus over y plus times sine theta e raised to minus I phi raised to L minus m. And that is 1 over L minus m factorial. And d by x is cosine theta, so d by d cosine theta is to m. And this is cosine square theta minus 1 is to 1. If you don't like the idea that what do you mean by d cosine theta, write it as d by dx, and at the end substitute x equal to cosine theta. So first take all the derivatives with us, then substitute x equal to cosine theta. We just have to collect things together at this point. So write it as m equal to minus L is plus L. Let me collect the plus first. So I have y plus, that is a 2L, and it's in the denominator, so L minus m. So this becomes L plus m. 2L minus L plus m, that's L plus m. Remember that it's in the denominator. Next, since this definition has an L plus m factorial, I'm going to provide that n extra, L plus m factorial. This is not there coming from the previous line, but I'll provide that anyway. So what did I provide? So I rewrite that as L plus m factorial. This L minus m factorial, I'll write it as into two pieces. L minus m factorial here and L minus m. Y minus it's already, there's only one place it appears, so that's L minus m. So I've taken care of plus minus y plus y minus, and now let's worry about e raised to I phi. So I have e raised to I phi, and e raised to I phi and sine theta. See, like if I were to put this in the denominator, that comes in one form. That's L and it's in the opposite order, right? E raised to I phi, so it is L minus L plus m. Because this is really sine theta in the numerator, but I'm having it in the denominator. So overall, they come out to be as plus m. So I've taken care of this, and eventually it is just this coming in. So it is for once, let me, yeah, I think that this is okay. When I write it on the other side, I will write it in that L minus m. And I did not write the 2 raised to L. I'll write that in here, 2 raised to L and L factorial. Because remember, legendary polynomials have the 2 raised to L and L factorial, so it's good to recognize that that is that feature of legendary polynomials. So what is your, if I were to compare it with this, what is your y ln theta? So that's your spherical harmonics of order L and m theta phi. I can read it out. There is a 4 pi over 2 raised to L, which I couldn't capture. So it is 2L over plus 1 over 4 pi. So that's kind of a normalization constant that begins with the rest, everything starting from this point is for once also write this in this form so that you know what often you will see this in this form also. These are practically your wave functions that show up in your hydrogen atom constructions, the energy level constructions that you do. It assumes that this has been already defined, and somewhere in the differential equation you will say that that's y l m, and this practically decides your SPDF shape of your orbitals is decided by this, but it has nothing physical in it. It is very mathematical, and the way we constructed it, it did not depend on the physics at all. So give me any function, and it can be expanded in terms of this. It is pretty much like taking the sphere and use some latitudes to cut it out. This is your sphere. How many L's you take decides how many lines. So these are your L's. I say L's because how many of them you take, it's like Fourier transform. How many sine functions you use to write your sound makes it more and more precise. So how many L you take makes your function more and more precise, and your M is going from your north, so that's your longitudes. So how many of them? Often you call this harmonics, spectral harmonics, because you're doing exactly what a Fourier transform would do, and on a number of line. So that's YLM, and now let's proceed and do something else with this. So now from this point on, I assume that there is YLM, and I want to give some properties which I'll use. I'll need this. That's YLM, and its definition is to maybe very quickly calculate a few of them just to show that how it works. Let's do y00 theta phi. So L equal to 0, M is equal to 0. Okay. Got some sense that it was not.
It kept making noises, I didn't know what it was doing.
So put L equal to 0, M is equal to 0, that's 0, so it's 1 over 4 pi. L equal to 0, so this is 0 factorial, that's gone. L is equal to 0, M is equal to 0, everything is gone, so that's just 1 over 4 pi, right? So it's a constant. So let's do y 1 0, let's say, theta phi. That can be yeah, I'll just do y 0, yeah, why not? Plus 1 y 1 1. Very quickly try to do this. And this is also related to the multipole expansion. You will see that structure also coming up. But at this point, these are just polynomial. So L is equal to 1. So that's 3 over 4 pi. L is equal to 1, M is equal to 0, so that goes away. M is equal to 0, so d by dx of let me just wait. So d by dx of x square minus 1. D by and 2 raised to 1. I think that's correct. And x has to be replaced with cosine theta. So this is 2 times. When I take the derivative, it is 2 times x. 2 cancels out, so it's just x. So it is 3 over 4 pi cosine theta. Remember, your dipole moment has this p dotted with r coming up, so that is that cosine theta drawing up. These two are related. I'll just do the plus 1, so 3 over 4 pi again. Now it's 1, so that's 2 factorial, and that's 0 factorial. And now 1, so this is e raised to I5 times sine theta. And L is 1, M is 1, no derivatives, so cosine square theta minus 1 raised to 1 over 2. Better? Cosine square theta minus 1 is sine square theta with a minus sign. This minus, I suppose. Minus 3 over 8 pi sine theta e raised to I5. And this one will be 3 over 4 pi. Again. Now it's minus, so this is 0 factorial, this is 2 factorial. E raised to, this is minus 1, so it's sine theta over e raised to I5. It's basically minus I5. L is equal to 1, so this is d by dx whole square. X square minus 1 over 2 by 1. 2x, and then take the derivative again, that gives you a 1. So this whole thing is 1. And it should be, so there's a factor of 2, so that makes it, that is plus, I suppose, plus 3 over 8 pi sine theta e raised to, no, sine theta e raised to minus 3. And you notice that components coming out, if I add these two, that is a cosine phi, and if I subtract these two, that is a sine phi. Those are all features that that's a simple way of explicitly seeing the spherical harmonics. They're polynomials in angles. And that's why they're called, since they're in angles, that's why it's called spherical. Some properties of this, which you see it in your homework, but then I make it optional, so you don't see it in your homework either. If you do your homework, the ones that I do not ask you to submit, the expectation is that you go through it at least. If not, I'm just saving your time by not making it for submission. But these are the results coming from your homework. The first one is let's say completeness relation. Remember, what is any unit vectors has a completeness relation, and an orthogonality relation. We studied this long, I think, in the first few weeks. If I were to have two vectors as my vectors, unit vectors as I, EI, it doesn't have to be normalized. Then I have orthogonality is given by dotted with EJ. Will be delta IJ. That's orthogonality. Like think of I hat, J hat, that's the best two of them. If they are the same, they are one, otherwise it is zero. But more importantly, which we don't use in the undergraduate level too much, is the completeness relation. And that's this. There is no operation. This is a tensor product, an outer product if you want, that's one. Always. If you have a contravariant set of unit vectors, covariant set of unit vectors, they will always give you one. This is completeness relation. That's orthogonality relation. YLM form a complete set on a function or a function defined on the surface of a sphere. So that's the idea of completeness relation. We have to show that somewhere else. That's in your homework, which is optional. Again, I make it optional, but the expectation is that you go through that whole derivation. It's a lengthy derivation, but nevertheless expected outcome. So the completeness relation nevertheless is that if I were to sum over all the unit vectors, right, in two orders. So this is now L going from 0 to infinity and M going from minus L to plus L. So if I add up all those unit vectors, I will get a 1. But 1 now, this is in a function space. It is an infinite dimensional space, so it becomes a delta function. So this is equal to YLM theta phi and YLM theta prime phi prime. So I'm summing over, but notice I is the same, but these two vectors are different, right? This is a dyadic, so it's a dyadic in the theta phi parameters. So that dyadic can make it a complex conjugate. This is equal to delta of theta minus theta prime. Only the one contributes a diagonal structure, and delta of phi minus phi prime. And for making the delta function better, put in that's your area element coming in. So it is 1 over the length in the theta direction and 1 over the length in the phi direction. So the length has that sine theta piece to it. Think of why the surface area has a sine theta r square term. So that's your completeness relation. I won't say anything more on that, but I'll use it and show you how it is being how it is used. If I can finish that whole derivation. So second is orthogonality. These are always the two most important. By the way, this immediately tells you the statement is that once you have this, any function on a sphere can be expanded in terms of YL and theta or phi. That's a statement. It's like saying if this is true, any vector can be expanded in terms of its components. If I know the components, I know the vector, I know the vector, I know the component. So there's a one-to-one relation. And orthogonality conditions is opposite. Now you integrate over theta phi. So notice here I was kept the same and the vectors were different. Here the vectors are dotted, I and j are different. Do the same thing in here. Now do the integral. So do the integral d theta sine theta and d phi. This is 0 to pi, 0 to 2 pi. Often you say this is the solid angle integral. So that's sine theta theta phi. So is this, what is that equal to? If I integrate over the whole solid angle, what do I get? 4 pi. That's the surface area of a unit sphere. So that's 4 pi. Very good. So this one now I have to leave the L and L prime alone. So I say L M theta y star y L prime theta prime of theta phi, that's equal to delta L prime delta M prime. That's your orthogonality condition. You can use these two, but I'm stating this as a separate statement. There's also this differential equation that the spherical harmonics satisfy. And that's equal to 1 by sine theta, d by d theta, sine theta, theta plus. What is that equal to? Anyone?
Is it
Zero.
0? No?
uh
See this in quantum mechanics and electromagnetism, you must have seen. What is that
that's
equal?
L squared, so L times L plus one
Very
y
good.
Ln.
Very good. So this is L, so this is an eigenvalue equation. Y L M theta phi. So this is the operator whose eigenvalue is L alpha plus. See, those are your eigenfunctions, right? In matrices, you talk in terms of eigenvectors. So these are your eigenfunctions for that operator. And let me just make sure there's a, oh, there is a minus sign. So right, there is a minus. Okay. That's your differential equation. So let's instead of deriving this again, this is all part of your homework. It's not very hard to do this, but since I go through every step in your homework, it looks lengthy. But every step you should be able to do it, and I expect you to be able to do it. Everyone expects you to be able to do it. You should be able to prove the orthogonality of a spherical harmonic. You should be able to show that it satisfies this differential equation. You should be able to use the completeness relation of a spherical harmonic. Yeah, in fact, you're already using it if you're doing quantum mechanics, if you're doing electrostatics, you've already used this in various places. Okay. Here, the next 15 minutes, I'll try be ambitious. This is called the addition theorem. For spherical harmonic. As I said, name for trigonometry. Is that spelling correct? Maybe O. You have sine of theta plus theta prime. What is that equal to? Sine theta prime plus. So let's say let's do like this way. This is an addition theorem in trigonometry. Give me two angles. I will give you sufficient functions where I will split the theta and phi. So here theta and phi are separately coming. Here they come up as a sum. It's better to write this as minus because this will be, it doesn't matter plus or minus, right? Oh, let me write it as plus minus. Yeah, why not? Right, that's your relation. We will see a similar thing for spherical harmonics, and it will show that it is legendary polynomial that we have already seen, which we will begin by saying recall. This was your classic, everything begins from this, your electric potential due to a point charge. What is this equal to? If I place my R prime on the Z axis, what is this equal to? What is that series? There was a series, remember? L equal to 0 to infinity. No?
Yeah.
It's to L. And what is that?
The Legendre polynomial.
That's the definition of Legendre polynomials, right? So this is the Legendre polynomials, and let me say this is cosine of gamma. Cosine of gamma is nothing but R hat dotted with R hat. The idea is that all the radial part, remember, whenever you're solving differential equations, you want to pull out all the radial dependence and the angular dependence. You're saying that all the radial part is in here, all the angular part has been separated. That's primarily what you're saying in this, but it's a sum. So if you were to do it for one L, then you're pretty much separated. But otherwise, it is not separable. Like, and only then you can do the solve the differential equation. What is the equation satisfied by this equation? So this is del square. This is your Maxwell equation, right? Maxwell equation for a point charge. That's a Maxwell equation tells that electric potential satisfies your 1 over epsilon naught times the charge density, right? So this is the electric potential due to a point charge, except for Q and epsilon. So that also tells me that this must be true, 1 over R minus R prime. Remember, for a point charge, rho is Q over epsilon naught times delta function. That's must be true. So if I were to strip out, and phi is 1 over 4 pi epsilon naught, Q over 4 pi epsilon naught. So there is Q over epsilon naught on both sides. So this must be true that 1 over 4 pi also has to be provided there. This must be true. That's a differential equation satisfied by that function. Explicitly expand this out. What is the Laplacian in spherical coordinates? Anyone?
1 over sine theta partial with respect to theta sine theta function. Oh, that's right.
What? So that's 1 over sine theta. Yeah, plus 1 over r square sine square theta. One over 4 pi. And this is equal to delta of r minus r prime, delta of theta minus theta prime, delta of phi minus phi prime divided by the area element on the surface of a sphere. That's r squared. Sine theta. That's your explicit way of writing this. But we know that if I were to now notice, in general, this equation doesn't separate. Like this doesn't separate into r and theta phi. Right? So this is only under special conditions it separates. It's the modes. Each L mode separates. So what I'm going to do is that let me call this the Green's function. Remember, whenever right hand side is a delta function, then I say it's a Green's function. Let's call this G of R prime. Right? That's a function. And expand this as this has an angular part to this and a radial part to this. So maybe explicitly write that. So it has r prime and theta theta phi theta prime phi prime. The three spherical coordinates from R, three spherical coordinates from R prime. The theta phi prime alone, because this differential equation is theta phi alone, I expand it in terms of spherical harmonics. So this is equal L equal to 0, infinity. M going from minus L to plus L. And the coefficients, so this is your unit vectors, y, L, M, theta phi. Right? That's any vector can be expanded in terms of unit vectors or components. This is my function, that's my eigenfunction. Its components, I have to find that out. So if I find them, I'm good. I'll call them y, L, M. Whatever is not there, I'll put it in. Except for theta and phi, it depends on everything else. These are the components of my function that I'm interested in. I'm interested in expanding this out. So I expanded this out. These are my components. These are my eigenfunctions. Any function can be expanded in terms of its eigenfunctions. These are my components. If I find them, I'm home. I have found my solution, right, or an expansion in terms of that. Substitute this in there and use my completeness relation. So use this on the right side. So notice theta prime, phi prime is there up here. So I can use that on the right side and on the left side. So for once, I'll write it down, sort of rewriting. Theta, theta, theta. Square, phi square. And now sum over L and M, GLM. This is what I'm interested in. Phi L M theta phi is equal to on the right side, do the same. On the right side goes here. This is delta of R minus R prime over R squared. And this is sum over L M y L M theta phi. Both these are two vectors written in terms of its components. When there are two vectors that are equal, their components must be equal. Right? If I say that is 2i plus 3j is equal to xi plus yj, this implies that x is equal to 2, y is equal to 3. Right? If I can write two vectors, so on the left hand side I have a vector, on the right hand side I have a vector. If they are the same, then it must be true that each component is the same. But for that I have to first act on this, so bring this in. So what I learn is that I have to bring this summation out. So I have 1 over r square right here. This is plus 1 over r square. Right, so minus L into L plus 1 over r square. Acting on GLM, which depends on r prime, theta prime, and phi prime, is equal to delta of r minus r prime over r square. Often when you're solving differential equation, you use the idea of separation of variables. This is an explicit separation of variables. I said, how did I separate them? first I said I want to expand the function that I'm interested in terms of the angular eigenfunctions, whatever the coefficients are, now satisfy this. This is a differential equation in one variable, much more easier to handle than spherical harmonics where there were three of them. We use the spherical symmetry, or I shouldn't say spherical symmetry, whatever is the angular feature has been removed completely. Yes.
So could you explain a little bit more steps in
Yes.
that line?
Okay.
Yeah.
Let's put this, operate this out, take this inside. There is no LM in this whole thing, so I can bring the sum all the way out. Yeah. Okay, so this is sum is being brought out. L equal to 0 to infinity. M going from minus L to plus L. Minus 1 by R square, d by dr, R square, d by dr, they all act on GLM. This whole thing acts on YLM. That's a differential equation for it's an eigenvalue equation for YLM. So this gives me this whole thing acting on YLM gives me minus L times L plus 1 over R square times YLM itself, but I'm going to write that on the right hand side. Is that clear? Yeah, right. So, and there are variables in here, but let me not talk of that. And now this is delta of R minus R prime over R square times LM YLM theta phi YLM theta prime phi prime. With me? Now, these are eigenfunctions, right? These are unit vectors if you want. Right? But whatever sits on the front must be the same, whatever sits on the front of that. Right? So that's the idea of vectors. Whenever we compare vectors, 2 is equal to x, 3 is equal to x, except that these are infinite in number. But each one, that's the idea of completeness and orthogonality, that I can compare one to one in there. That's a basic idea that we are using in match that. So I can basically bring the whole summation down. And now I have 1 over R square. R square. This is GLM. I'll give you a quiz. Theta prime, phi prime is equal to, I'll write one more step. What's on the right hand side? Is there anything else remaining? Right hand side? These are my eigenfunctions. The other part has to stay. Okay. R square cancels out. Let me do one more small feature. D O M prime theta prime phi prime is equal to delta R minus R prime times Y O M theta prime phi prime. That's a differential equation I have to solve for R. This is a Green's function equation, right? There is a delta function on the right side, except for the fact that there is a coefficient also in front. Whenever it's a Green's function, there is a continuity condition available. How do you find the continuity condition for a Green's function? You integrate it. When you integrate it, the right hand side gives you a number because it's a delta function. It gives you a number. So this is your quiz. Find the continuity condition at R equal to R prime. Remember, I was very disappointed with your continuity condition in the exam. So derive the continuity condition. So what you do is you do an integral on this in R prime, sorry, R, going from R is equal to R prime minus a small constant, that's not dielectric function. R prime plus epsilon, as epsilon tends to infinity, epsilon is greater than 0 and epsilon tends to 0. You do this integral on the left side and on the right side. That gives you a condition at R equal to R prime. Since you are capturing the pole of this delta function, that will give you 1 and this remains. So this gives you a condition on the Green's function at R equal to R prime. And that is necessary to proceed and solve this equation. And once you solve it, it's only a few steps. We'll get the addition theorem, which I will come back and do on Monday. Your homework should not depend on this. I haven't completed spherical harmonics in the sense that I want to complete addition theorem, but your homework should go through. It's relatively straightforward. You just have to use pretty much work with simple polynomials and using the spherical harmonics. Again, this is quiz. And if you want to do more, go ahead and solve this differential equation. Anyone wants to guess this solutions here right away? What is the solution for GLM if it is 0? Remember, delta function is 0 everywhere, right? Except at R equal. If this was 0, what solves this? A very straightforward solution.
One. So -1 plus 1.
So the idea is d by dr, r square, d by dr, right? So of f is equal to L into L plus 1 of f itself. What function, when you operate it with this, gives you L into L plus 1? Notice there is an r square in the numerator, there is 2r in the denominator. So it will be a power series, power function. In fact, the solution is just r raised to L. You bring down 1, r raised to L minus 1, that's one derivative, then you add plus 2, and then you bring down, so bring down again, so that's minus 1. So that's a solution. And it turns out, so r raised to L is a solution, and it turns out that 1 over r raised to L plus 1 is also a solution. That has to do with the inversion theorem. Laplacian always satisfies the inversion theorem, where everything, if you have heard of inverting a sphere, yeah, that's also a quiz. Look up a video on what is it called? Inverting a sphere. I think it's just called inverting a sphere. It's a very beautiful video, elegant video. And the question is, can you, you have a football with some rules given, can you put inside out? Like the inside part of the football should come out and outside goes to inside. And there's a nice video. It is a theorem basically in mathematics, but it is elegant. That's basically the idea of, I think it's called inversion, but check it out. Yeah. Thank you. Stop here. You guys have a plus. Oh, a long time ago.
Nick, he does voiceovers and fun stuff.
Thank you.
No, don't look up video.